Please. Thank you. Thank you for the gentle introduction and the invitation. Yeah, the goal here is to give you some, it's a very generic title. One of the goals is also to educate you that DFT is a very interesting problem from the mathematical side. And it's, you don't have to understand much. It's a nonlinear eigenvalue problem. That's it, okay? But first, let me motivate why I'm interested in this topic since now about 10, 15 years. So I have two keywords, Navier-Stokes and density functional theory. I have two libraries or bibliometric measures. One is Google Scholar and the other one is MathSciNet. Google Scholar represents the entire scientific community in this kind of picture, and MathSciNet, this is a subset of mathematicians working on this problem. So if you type in Navier-Stokes, it's very prominent, many engineering applications, etc., you get about 1 million hits. So what do you think, how many hits do we get for density functional theory? Who is for more? Who is for less? Okay, let's take a look. Wow. Yeah, it's an important problem, and many scientists work on this. Yes?
Is there another problem with the same name?
With the what?
Like, does another discipline have a similar problem with the same name?
No. I give more, there will be more substance to underline my claim. And you can look yourself on Google Scholar, everything is public. And now the big mismatch is this one. So the subset of mathematicians working on the respective problems, density functional theory is very much underrepresented. Okay? And I said it's a nonlinear eigenvalue problem, or more correct, a nonlinear eigenvector problem that needs to be discretized. We need to have numerical algebra solvers that converge confidently, etc. So there are many numerical analysis, many applied mathematics questions there, uniqueness, well-posedness, etc. But somehow, historically, applied math is more inclined towards engineering science. And even if you look at supercomputing sectors, you can take one or the other, the numbers are always similar. You have a huge amount of CPU hours that go into these disciplines that use these molecular levels, among others based on density functional theory. And many challenges of this 21st century, like energy storage, drug design, quantum computing, finding new materials, etc., are related to models on the molecular level. Further, 2 of the 10 most cited papers about DFT, according to Google Scholar, with more than 100,000 citations, are 2 of the most cited papers are about DFT. So no, it's not just a different, the name has a different community behind. No, it's really the density functional theory that is so prominent in the applied sciences. And for what concerns us, there's a small subset of mathematicians working on this, very open towards interdisciplinary applications. We founded this GAM activity group, Modeling, Analysis, Simulation of Molecular System, in 2017. So next year we'll have our 10th anniversary, and everyone is welcome if you feel that there's some benefit joining this activity group, and come to our meetings. Okay? So, with this teaser, let me go through the outline. I want to give you a first impression what is electronic structure calculation, what is density functional theory. So I really designed it a bit lecture style, so I don't want to spend 50 minutes about the top-notch research, but rather I would be very happy if you pick up some elements, what is DFT, why is it important, etc. As I said, we need to discretize it, and we can speak about a posteriori error estimations, and if time permitting, also interpolation of density matrices. As I said, I want to bring you a bit closer this fascinating subject, and at the end, some elements of research. Okay, I'm very grateful for Johan and also for Moritz to give a very good preparing the floor in the morning for this talk, because now I want to start with the classical model for the hydrogen atom. And why do we need quantum mechanics? So, we say we would like to model an electron in the presence of a proton with a classical model. Okay, so what will you do? You take an electron of mass 1. I mean, of course, we're mathematicians, so we take the according units, so everything is 1 of -1. The charge is -1, and we have 1 proton of mass mp. That is substantially larger than the mass of the electron. This is known, and it's positive charge. And since the mass is way bigger, we can say this moves way faster, and I clamp this at the origin. And then you can say, okay, what do I know from classical theory? So you come up with a phase space Hamiltonian. X is the position, P is the momentum. Same notation in Johann this morning. So you would have a kinetic energy term here, and here an attractive potential. This is 1 over x Coulomb type potential like this. You can call it sometimes V of x, and that would be the model. Okay, then you can ask yourself, well, what is the solution to that? And you can go into the dynamic picture, which is not complete though, but you could say, okay, I take some initial condition with small amount of energy, and then the issue is that if you would start here with this ball, it starts to spin faster and faster and collapses to the proton. And in addition, this is not the full picture because you also have electrodynamic effects, you have radiation of energy, etc. I'm just here very briefly stretching on the surface. You could also look at the stationary equations. You take the Hamiltonian, you differentiate with respect to momentum and the position, and while this is not possible with this kind of potential, and it reveals that the Hamiltonian over the phase space is unbounded from below. So you can find sequences somehow such that the energy goes further down and down. Okay, so this means if you have a Hamiltonian that is not bounded from below, there's an unstable configuration, and this motivates the introduction of quantum mechanics. Now I'm having a little bit a different picture to present it to you than this morning. It's more axiomatic. I say I do a quantization, and the state is no longer described by an independent choice of position and momentum, but they're somehow coupled. And I cannot tell you the electron at this location, rather give it a probability distribution about finding an electron in a certain volume. And this probability distribution is the psi, the same psi, just that I write it time independent. Square is the probability distribution. If I take the Fourier transform of it, I interpret and say this is the probability density to find the electron with the momentum p. Okay, in Johann's notation. But you see, since these are the two functions, one I have the function, one I have the Fourier transform, there's a coupling between the spatial distribution and the momentum distribution. And this ultimately, with a bit of probability theory, gives the Heisenberg uncertainty quantification. You cannot choose independently what happens in space and in momentum. They are coupled through the same wave function, and once you have the modulus square, and once you have the modulus square of its Fourier transform. Then you can take the classical Hamiltonian and take the expectation value. Say, I'm taking the expectation value to find my electron, or to have the kinetic energy times the probability to fact that the electron has this value, and the same here with the potential. You can say this is my energy, just the expectation value in a probabilistic sense, and then use some tricks from Fourier analysis that we saw this morning, that if I multiply the Fourier transform by p, I get a minus I here of the Fourier transform of the gradient. So, we can start here with p squared, psi hat squared, is kind of this term. I take the p in the modulus. Now I use here this statement here. I don't care if I have the absolute value of the modulus here, the minus I, let's kick it out. And the end, you use that the Fourier transform is isometry, so it has the same L2 norm. And I go back from the Fourier to the real space psi function, and therefore I can write my energy in this form, and that's the form you have seen earlier this morning. This is the kinetic energy, and this is the potential energy. Okay? In consequence, if you have this model, the energy is well defined and continues over H1 functions. It is bounded by low by -1/2. So in consequence, you can claim that the hydrogen atom is stable. You know its ground state or the eigenfunction with the smallest energy, and the stationary equations is this eigenvalue problem. Okay, this is the picture for one electron. Now, a molecule has several atoms and several electrons, and I'm not going into full details, but we assume the so-called Born-Oppenheimer approximation. So that means that the nuclei are considered classical particles. For very heavy nuclei, there are quantum effects, etc. No, sorry, I'm going towards Dirac. The full picture, the nuclei, protons are also quantum particles. But since they're very heavy, you can assume them to be classical. But the electrons, you still consider them to be classical quantum particles. Yeah? So I have a wave function that is a psi that depends on the position of each electron. So this is a position in R3, and you have as many as electrons. N is the number of electrons. Further, you have the nuclei. There are positions R1 to Rn, and they have a charge Z1 to Zm respectively. Since electrons are fermionic particles, the Pauli exclusion implies that the wave function must be antisymmetric. What does that mean? If I do a permutation here, so you can think of just swapping two positions, you must have a -1 here. If you swap twice, then you got a +1. So this is the signature of the permutation P. Okay, this is the intrinsic nature of fermions, and electrons are fermions. So here, with this X for us is the antisymmetric subset, or the subset of antisymmetric functions that are H1. And for sake of simplicity, we do not speak about spin here. Real chemistry is about spins as well, and we ignore it here. An important notion is the electronic density. That is, if you average out or integrate all but one variable, and multiply by n, and this is the distribution of electrons. So you see, if you integrate the rho over x, you have the full integral of the psi, and this is again a probability density function is equal to 1. So if you integrate the rho, you should get n, and this is the total charge of your system. Okay, now the full many-body Schrödinger equation is a bit complicated, because it's high-dimensional. But mathematically speaking, we want, for a fixed configuration of the nuclei, to find a minimizing wave function, if possible, an argmin and not an arginf, that is of norm 1, that minimizes this energy. This energy now is a sum over each of the particles. Each of the electrons has a kinetic energy. That's a strong form of the kinetic energy from before. And if we do a Laplace sub xi, it's the Laplace with respect to the xi or xj variable. So here, remember, this is a function that depends on n times 3 variables. So x, the Laplace with respect to x1 would be the Laplace with respect to these three coordinates. Yeah? Okay. This is the interaction between the nuclei. The nuclei, again, this is classical Coulomb. That's a potential generated by the n nuclei at position R alpha with charge Z alpha. They generate the potential, and the electrons feel that potential, and each of them you evaluate it as xj. And then this is also the electron-electron repulsion, because two electrons are same charge. Classical picture as well, they repel each other, right? So this is like a classical Hamiltonian, but afterwards we multiply it with the probability density, etc. This is just electron-electron interaction, or two particles of same charge. And then here, well, you can here look for the first order optimality condition, or Euler-Lagrange equation. And since you have a non-constraint here, you have to do a Lagrange approach. You introduce a Lagrangian, and you find out this is equal to a linear eigenvalue problem. Here it's completely linear, but very high dimensional. If you have 100 atoms, you have 300 coordinates. Yeah? Wave function depends on 300 variables. And 100 electrons is not that much. Okay. So unfortunately, the Schrödinger equation is too difficult to solve. There are very few ansatz that try to tackle this high-dimensional object here. There are ansatz, but most of the time not. There are different ways to deal with this. One is density function theory, but there is post-Hartree-Fock method, quantum Monte Carlo. There's a full zoo of different methods. I'm going just in the following part, DFT. Yeah? DFT is a good compromise between accuracy and computational efficiency. Yeah, okay. So we will focus on DFT. Okay. So just in short, DFT, in contrast to the Schrödinger, or are there any questions so far? Maybe we have time. I was told that the next talk is cancelled, so we have all the time. Okay, then, if not, yes?
Where are the charges of the nuclei hidden?
They are in the potential here, Z alpha, that is felt by each. So also if we speak about data, there's only few data. It's just the position and the charge. And the rest, you know, this is kinetic energy, has no kind of external parameters. This is just self-interaction between electrons. So the only data is in here. Yes?
And the spins would enter with an additional term, or?
The spins in this... Okay. So in some models, closed shell models, you would have that always a spin up and a spin down. They occupy one of the orbitals. And then you have the same question, like the same story like this. It's just that instead of a charge 1, you have 2 times the charge. Because you know every level is occupied once with spin up, spin down. Yeah? And that is the same thing. Then for complicated chemical systems, you have to account for spin. Then the wave function, wait, where did I go? Here, not only depends on the position, but also by a sigma I, sigma 1 to sigma n, and sigma 1 can have 2 values, spin up or spin 2, spin down. Yeah? Okay, yeah.
I have a question which might not, I digress a bit, but I'm curious. So if I have a somewhat low dimensional system, maybe 3 electrons, and I really want to compute the wave function. And so how would you enforce numerically this antisymmetry? Is there...
There is a concept in the Hausdorff theory is you use, like you can use a symmetric, you can have a tensor product.
Right, yes.
You can have a symmetric tensor product, or you can have an anti-symmetric tensor product, and that's a determinant.
Right.
You can write it so. the simplest ansatz in the Hartree-Fock theory is you write your wave function through a determinant of one-dimensional functions with n variables, and this is like a rank 1 approximation, so to speak, but with in an antisymmetric world. And then you can try to minimize exactly this energy here, but here you restrict it to be so-called Slater determinants, and then you find the Hartree-Fock equations. And then there's this whole zoo of post-Hartree-Fock methods, which first do this Hartree-Fock model, and then you get a family of orbitals, and with always choosing n out of this many, you can build Slater determinants. They are all antisymmetric, and you can build linear combination of those again as approximation space, and then you're intrinsically antisymmetric. Okay, but now let's move to DFT. It's a low-dimensional model in the sense that my unknown depends now only on 3 variables. It's a so-called mean field model, and it's a solution to the high-dimensional Schrödinger equation. In the sense, I'm going to precise. So a mean field means that each electron is only exposed to the others in a certain average sense. And mathematically, it's a nonlinear eigenvalue or better eigenvector problem. So the price to pay to go from high linear model to a high dimensional model to a low dimensional model is to introduce a nonlinearity in your model. Okay, so let us first take omega to be a bounded or unbounded domain, and we consider L2, the space of square integral functions, and we denote the inner product and the norm just like this. If there's no kind of subscript, it's L2. Then you can introduce H1, and H curly H is a subspace that encodes the proper boundary conditions. There are different choices, and you can look at this kind of infinite dimensional Stiefel manifold. So you take n copies of H, but they need to be pairwise orthonormal. If you have such a state, phi, you can model the density, the electronic density, as the sum of the phi squared. And then you can define an energy for such vector of H functions. And then here we have a sum over the different phi's and the kinetic energy. So you can somehow associate a phi to each electron. So n is the number of electrons. Every electron has its eigenfunction. This is the kinetic energy of the ith electron. This is again the external potential, that's the same before. And you can rewrite this, I mean, you could also rewrite this here in a sum and take the sum out, and then there would be here phi squared. Very similar to also Gauss-Spitaevsky. Then this is the interaction, the Coulomb interaction between the two densities. So it's the density, ρ2, interacting with this what's called Hartree potential. The Hartree potential is nothing else than the solution to the Laplace equation in 3 dimensions. So here I take the full domain. So the solution to the Laplace equation here in blue can just be written as a convolution with the fundamental solution of the Laplace equation. But basically this is the potential, electrostatic potential generated by ρ1. And this is really a classical term. If you are given 2 electronic densities, also in the classical sense, this is the interaction energy. And then here, this is the critical term. The devil is in this exchange correlation functional. Formally, there exists an exact exchange correlation functional such that if I minimize this, blah, 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 or this energy, the whole, or if I minimize this energy, then the corresponding ρ that I find corresponds to the one if I minimize the Schrödinger equation. But unfortunately, it's not a constructive proof. Its explicit expression is unknown. And there are many ansatzes and models that try to come up with good functionals. But it's very challenging to have a good model here. Okay, now about different boundary conditions. You can have a periodic setting. So your potential is, the dagger means periodic. You have some crystalline structure, you have some bumps repeated. And then you look here at the periodic space. Or this is more physics and material science, where you have crystalline structures, solid states. Or you look at the molecules, where you have kind of atoms and molecules, and that vacuum beyond. And then this is kind of the full R3 or RD, if you want. Good. Now, we are interested in minimizing this energy for a phi that belongs to this kind of Stiefel manifold. And you can derive the Euler-Lagrange equations, meaning you look at introduce a Lagrangian and you look at critical points of the Lagrangian, and then you come up with this formulation. We want to find the smallest eigenvalues, lambda 1 to lambda n, and the corresponding eigenfunctions, such that this equation is satisfied. So here, these are linear terms, kinetic energy, the interaction with the external potential, and then this V rho, where this is basically just the rest, and rho again is the sum of the phi squared. And I might call now the phi orbitals, that's just natural language, the orbitals of the electrons. Okay. So, assumptions, the objects are smooth enough such that this is really a mapping from H to its dual. So you can also, since it's a Hilbert space, apply the Ries theorem. We need a gap, because when I say the smallest, I need a gap to the next one. Otherwise, what are the smallest n eigenvalues? And this typically arises for insulators, or that's how insulators are defined. There's a gap. For metallic systems, this is not the case. Okay, gap combination, and also for nonlinear, or for energies that are not necessarily quadratic. If I look at the linearized or the eigenvalue problem, and I pick the smallest n one, and then I take this function and put it in the energy, there is no guarantee that maybe if I would have skipped this and take the n plus 1, take the corresponding orbital and I plug it in here, that this energy would be smaller than the one with the first n. If you have a quadratic energy, this is natural. But for nonlinear models, this is not clear, and that's what's called the Aufbau principle. And we assume it here. Good, this is some weak setting, I think it's clear. Okay, so just because we spoke about a lot of Grassmann this morning, Grassmann can be seen somehow, although it's completely physically a different scenery because it's about bosons and this is about fermions, you can put it in this framework. This is the DFT energy, and this is the Grassmann energy. I assume now only have n equals to 1, and so my Stiefel manifold essentially becomes the unit sphere in the Hilbert space H, and this is the GP energy that we saw many times this morning.
Sorry, I'm confused by the notation. So, I mean, do we still mean that we have, is n still the number of particles?
Yes.
But so you're, okay, so you're just focusing on fermions, so you know that the number of it will be the same number of particles as the phi.
So here is n is the number of electrons. And in fermions, they cannot collapse all to the same occupation number, but bosons they can.
Right.
So GP, you can derive this from the full, from the Schrödinger equation, but they can all collapse to the same state.
Right. Yes.
Because you have symmetry, and so this is not, this n here is not the number of particles.
But small remark, if you have one particle,
Yeah.
the nonlinearity is an interaction term. What is it? Oh, it's a mean field interaction with itself.
No, this n here in the GP, because it comes from here, it's lost its meaning, physical meaning is the number of particles.
Yeah.
It's just the way to go from here to here, I have to put n equals 1.
Okay, yeah.
That doesn't mean I'm dealing with one particle.
And
I
then,
just want to say that this is very similar to that. For instance, this term, and this is kind of, this could be identified with this. But since I only have one function here, I have to put n equals to 1.
so may I ask one
Yeah, sure.
question? Yeah, so is it clear that this correction term E subscript xc, that it only depends on the density?
Yes.
But
Yes.
Okay.
This is the so-called Kohn theorem that is stated by physicists, chemists, I don't know, many years ago. It gave also rise to the Nobel Prize, I think 98. That this can be written solely in terms of the rho. And it's a major breakthrough because it means you can formulate a theory that depends only on rho, and rho only depends on 3 coordinates. That made it so popular. Yeah. And then what we're seeing here is the so-called Kohn-Sham density functional theory. Yeah. Okay. And again, you can do here the Euler-Lagrange, and then you have here this Gauss-Bitaevsky equation where I played a bit. So the rho is just the phi squared. So here usually one sees here a phi squared modulus, but since now here my argument is a lot about the rho, I put here the rho. Okay? Back to DFT. This is a very important remark. So you have here this vector of H1 functions. Yeah? So you now take a unitary orthogonal matrix and you mix in these 5 functions with elements of this matrix. And you define a new vector of n functions. You plug it in the energy, you get the same energy. That means the energy is invariant under unitary transformation of your state. Okay? So it's very important. So this means mathematically phi is not a good representation of my solution because I have not uniqueness, right? I can just turn the orbitals. I mean, if this would be vector, right, this would be just a matrix multiplication, but these are no H1 functions, but you can think about vectors here. So I don't have uniqueness. I can turn these vectors as much as I want. I get the same energy. So the message is that the mathematically correct notion is indeed not the set of eigenfunctions, so the elements of the Shiever manifold, but rather the eigenspace. Because if I do this unitary transformation, I kind of just span the whole space. And you can associate this also, we'll see in a moment, with the Grassmann manifold. One can therefore reformulate the theory in the so-called density operator formalism. So instead of having this set of orbitals, I define the unknown by means of the spectral projector onto the eigenspace. My unknown is a projector that projects me on an n-dimensional space. In order to introduce this a little bit more rigorously, we need to define what is a trace or operator. So I take A to be a bounded positive linear operator. Then for any O and B of H, the trace is defined by this. Okay? You see, it directly generalizes the notion of the trace of a matrix if you take the canonical basis here. Okay. Since we have kinetic energy, we need also this condition. So these are the so-called finite energy density matrices. You see here GR stands for Grassmann. So this is a bounded self-adjoint operator on H, but we have eigenpotency. That means its eigenvalue are either 1 or 0. So it's a projector. its trace is equal to n. That means it projects on an n-dimensional subspace, and it has finite kinetic energy. So for every eigenspace corresponding to a set of orbitals, it can be represented by its L2 orthogonal projector onto this eigenspace, yeah? And this is this gamma, yeah? And it's given like this. If these are the orthonormal eigenfunctions, you build the scalar product, multiply with this, and that's the spectral projection of V onto this eigenspace. And so you can also give its kernel this gamma hat. Yeah? This is the sum of VIX, VIY. Why? Because this, as being the definition of the kernel here, we write it like this. We substitute this sum in here. And we see here we have the L2 scalar product. That's this term. That's the one here. And this one is remaining. So it is indeed, you can show this is a Seifert joint operator. It's a projector. You apply it twice, you get the gamma. Its rank is n because you have n orbitals. And this object is invariant under these unitary transformations because it represents a space, and the space is independent on the basis. Okay, so therefore, this gamma belongs to this manifold, and instead of looking for minimizers or infimizers of this energy, you can try to minimize the spectral projector by just saying, I'm minimizing here this operator A, the trace of A with gamma, and there's a nonlinearity through the row. So every gamma generates a row. Okay, this is a bit excursion to very elegant formalism that is, in my opinion, little known in applied mathematics, but is very powerful. Physicists use it all the time. And you can do numerical analysis with that as well. Yes?
Yes. And why is the trace of a gamma finite there?
This one?
Yes.
Well, I assume here that I'm in this manifold. So I have this object here.
Okay, yes.
And then this, I mean, if you look only in this object, so you have a finite kinetic energy.
Okay.
Yeah. Good remark. Yeah. Okay. This is still on the continuous level. This is like we spoke about the Laplace equation for half an hour and still did not discretize it, right? It's just about modeling. Of course, you can introduce now a finite dimensional subspace of this Hilbert space here and do the same in the discrete picture. Yeah? You find the first order stationary equation. That's actually what you solve afterwards. You need to have a good basis. Yes, it's a nonlinear eigenvalue problem. Now discretized. And of course, you can also have an approximate density operator if you want to see the full story in this picture. Okay? So, about the basis functions. So, assume we're in chemistry. So we are in the entire space. Yeah? And assume I know there's some positions of nuclei. They use some kind of ansatz that you have nuclear centric approximation functions. Yeah? So x shifted with this position here and potentially times a polynomial. Yeah? And here this exponential is either in x or in x squared. And then each of these discretized orbitals you write as a linear combination of these basis functions. In material science, where you have periodic boundary conditions, you take plane waves with here these g vectors on the so-called dual lattice. These are all points g such that my resulting function is periodic on my lattice. Not for every g you have here a periodic function, but certain points, and this is the dual lattice. Yeah? Then they look like this or like this, you do again linear combinations. you can derive your numerical or linear algebra equations, and they look like this. So here you see an ansatz of an eigenvalue problem. Yeah, the columns are the eigenvectors. S is the, you would call it mass matrix. Physicists you would call it, or chemists, overlap matrix. That's also a matrix with the eigenvectors, and this is the energy. It's just a diagonal. So this is an eigenvalue problem, but the solution matrix depends on the solution, or the Hamiltonian here depends on the solution itself. That makes it nonlinear. Yes?
So what you said the last two slides, that's like the initial guess, what they say when you take the function.
Here?
Yeah, no?
This is the ansatz. We don't know the C here. Right? You store them in a C.
Right. Yeah.
And then you basically, here, you test with test functions. And you write this down.
Yeah.
Yeah? You assemble what you would call stiffness matrix, etc. And if you do the math, you come up with something like this. This is orthonormality. This is a mass matrix. Yeah? That means two orbitals need to be orthonormal. That's the eigenvalue problem, but the operator here depends on the solution itself. And here you see, yeah, I just take here test and trial functions here and assemble those matrices. Yeah? Then in practice, while this is a nonlinear eigenvalue problem, the simplest version is I start with an initial D0, I plug it in here, I do a diagonalization of the Hamiltonian, I find a new CK and energy levels EK, I build a new DK, and I can do so. In practice, there are more sophisticated versions. Yeah? Use DIIS, direct inversion in the iterative subspace, Pulley mixing, Anderson acceleration, and a whole slew of methods and cooking. It's very expensive because the number of eigenvalues and eigenvectors that are stored is proportional to the number of orbitals, and the number, which is kind of also proportional to the number of atoms. Yeah? So the naive scaling is n to the fourth, yeah, to solve this. Yeah? Because you have dense matrices. Yeah? So hours per SCF iterations are possible. Yeah? Yeah, okay. Very quickly about the, this is the discrete version of the density matrix, this gamma. This is now just the matrix C times C transpose, and we assume for the moment that we have an orthonormal basis function, so this, the mass matrix is diagonal. Then you have here, this is symmetric, obvious, D squared is D, because you have the orthonormality condition, etc. You have trace of these n, so all the same properties, and you can associate it to the Grassmann manifold, which you can play around a bit. It's very nice, because the Grassmann manifold you can compute a lot. For instance, there is the Grassmann logarithm that maps you from the manifold to the tangent space through this guy here, or the exponential function that takes a tangent vector and maps it down to the manifold. And so, for instance, you can take here a D, compute its corresponding gamma, the corresponding vector in the tangent space, and take a T that goes from 0 to 1 here, and they take the exponential of it, like this, and it turns out that this curve is the geodesic on the Grassmann manifold. And these are not just kind of tools from pure mathematics that you cannot apply, but you can compute this logarithm and exponential by means of signal value decompositions. So it's case like n to the third. So compared to SCF, it's actually cheap. Okay. Good. I see I'm way too slow than I should, but I was told we have time. Sorry, I used this. But let's go now to plane wave DFT. So we do, this is just recap. These are the stationary equations. I've told all the ingredients already. This is just to refresh. These are the basis functions. Again, we have these plane wave Fourier modes that are periodic. And we use here a certain span of this to use the approximation space. Then this is the discrete formulation, and instead of writing it like this, you can put here the projector onto the subspace, discrete subspace, and here I have the original operator, and this is equivalent to this. It's a different way to write the eigenvalue problem. So this is a bit light in notation, so I could use this. Okay, now we make one very crucial assumption. We say that, so where is the energy? So where is the energy? Here. Okay, I skipped this part, but this is crucial. That's the energy in terms of this density matrix gamma. It's the trace here of this fixed Hamiltonian. This is the linear part, this is H, plus this is just the f of rho. Yeah? And in the following, we're going to assume that this f of rho is convex. What means convexity? That means that this is non-negative. Huh? Okay, so this is we assume this. Now, I'm writing energy differences between two gammas, gamma 1 and gamma 2, gamma 1. Just I write down the formula here for the energy. So in terms of a posteriori estimates, if you have to be awake 5 minutes during this talk, is now. Okay? There's the beef. So this is energy 2, energy 1 is this and this. Then use two ingredients. First of all, the trace of the two gammas, you assume them to be n. They have the same trace. So if you write here trace of a scalar times gamma 1, this is the scalar times n, and this term is equal to that term if you take the trace. They cancel out. Second point, you can write the derivative of f here as a trace of the potential times gamma. So that means this term minus this term, these are two terms, difference of this, can be written and observe, here's gamma 2 and gamma 2. Very important. Twice the same term. So this is exactly equivalent to this term. It's a equality. Now this term is more or less what's written up here, but with minus sign. So you can estimate and discard that. What you have written here is this trace minus this trace. Attention is gamma 2, gamma 2, but gamma 2, gamma 1, and gamma 2, gamma 2. Here the V is the same. Very important. Okay. Repetition. Now, assume an oracle gives us a mu such that this object here is non-negative. And you can always find a mu. If you choose it, you can shift. You can just shift here with a very negative number and shift it up until you're positive. But since the trace of gamma 1 is n, you can also rewrite it like this. So you see here also, whatever this number is, whatever n is, you can find this negative. Just choose it negative enough. If this is true, then we can also discard this term, because it's negative. Now, what is remarkable about this expression is that you can estimate this energy without having access to gamma 1. And of course, this opens the door for a posteriori error estimates, because you think this is the computed one and this is the exact one. Okay? So, if you have a conforming approximation, you can show that this energy is always larger than this one, just by minimization principle on a smaller subspace than the full one. And you can upper bound this by this, if you know the mu. And so here, but this is computable if you have gamma h, the numerical solution. And this then can be used to give also lower bounds of this of the exact energy. So we need to do an intermezzo for linear eigenvalue problems, because it turns out that what I'm asking here in terms of mu is something about linear eigenvalue problems. Okay, the question I was asking, by simplifying the notation a bit, how can we, for a given A and gamma, find a lower bound or mu such that this holds? And the application afterwards will be that we put in here the Hamiltonian. So if we consider this minimization problem, that actually means that we are going to minimize the sum of the eigenvalues. If you do this, we have seen this formula before. You plug it in, a bit technical details, you see this is the sum of the eigenvalues. So by this, we actually, the first order optimality condition is, again, find the lowest n eigenvalues of the linear eigenvalue. So what we learned is that here, this is the sum of the eigenvalues. And what's written here is nothing else than finding lower bounds of eigenvalues. We've seen this also in the morning. But we can only do numerical computations. So again, we have a discrete space, we have a discrete equation, and we have discrete eigenvalues. But now the question is again, how can we find lower bounds of eigenvalues, or more precisely the sum of the eigenvalues, if you generalize what Moritz told us this morning to the sum of eigenvalues. Luckily, years ago we solved this problem for linear eigenvalue problems. I'm not going into details, but you can here estimate this by an estimator eta squared. If you have this, you can take this and define its mu LB, and you can show that this is equal, smaller equal than 1 over n, the trace of this. You multiply by n, and you have solved your problem. But somehow, if you have a convex energy functional, and you have lower bounds for linear eigenvalue problems, you can have estimates for the energy. That's exactly the moral of the story here. Okay. So, as I said, for some approximate density matrix gamma h of the exact one gamma, we have that the error difference is bounded by this term, where this guy is obtained through that, and we can give confidence intervals. So this is a lower bound of the energy, and the upper bound is just by the discrete one. Okay, just, I said, I don't go into details, but I need to tell a little bit how we compute this lower bound mu. So, we have an eigenvalue problem like this. We have a discrete version here, and for any eigenpair of eigenfunction or an eigenvalue, you can define a residual, well, just standard residuals. So this is the residual of the eigenpair. But you can also take a cluster residual of this discrete density matrix. And this is an operator, Hilbert-Schmidt operator. You can take the two Schatten norm and you write it like this. Or you have also some A minus 1/2 weighted version of this, which is just this. Then, having defined this, the estimator is given by that. Okay? So there are some constants here. So the CH is this guy, and we need another ingredient that is a lower bound of the n+1 linear eigenvalue. But then this is computable to some extent, it's computable as well. So the leading term is clearly here. This is the asymptotically leading term. Okay. Now, I told you the whole story is a non-linear eigenvalue problem. So I write here the index of these so-called self-consistent field iterations. And here is the previous density. Now, let this to be a lower bound of this operator. Why is there shifting k? Because if you look at this problem, the eigenvalues we denote by k, where this is the k minus 1 here in. So this is natural that you go k plus 1. Then, this is just what I told you before. The error in the energy can be bounded by this guy, whereas this is now lower bound of the sum of eigenvalues of this operator here that is linearized at the kth iteration. Now with this you can even split it in two parts. So here's a k by adding this term together with this and subtracting. Then you have two error contributions that you can sum up, and you can show that if you don't have any discretization error, then this term must be 0. And if you don't have any nonlinear error in this nonlinear iteration scheme, so then this guy is equal to that, and this is 0. So you have two, they have their meanings. This quantifies the error from this discretization, and this the error from the nonlinear iteration. Okay. Now, finishing here with some numerical results, but we need to speak about two remarks. First of all, is it realistic that this convexity assumption? Yes and no. So not all practical used Sham, by far not all, are convex. This is more or less a toy model. You put this exchange correlation to 0, you can show it's convex. So we use it to do benchmark our code, etc. Some few models can be shown to be locally convex, but the big point is also the exact density function that we don't know. One can prove that it is convex. So a good functional is close to convex, but very many prominent ones are not. Okay. The second big issue is if you have looked into that one, I wrote the inverse of the operator acting on a residual. Now, a residual for source problems, it's the same as for eigenvalue problems, always leaves in the complementary space to the discretization space, because you have a Galerkin orthogonality or kind of principle that makes it the residual 0 on your finite element space or whatever. So this is a big issue because this a priori is in an infinite dimensional space. You can write it like this, and this is in the perp of the discretization error. So what we're doing is some kind of perturbative approach. You write the operator in terms of this is the one that is mapped onto the discrete space plus the other ones in a kind of block notation. You take here A0. Here you took the full discrete one that you've solved, and here this is just the diagonal one. So the Laplace operator in Fourier modes is diagonal one. This is just a scalar, it's also diagonal, and the rest you just take as a perturbation, and basically you argue about Neumann series, where this needs to be small enough such that you can expand it in Neumann series, and this is a 0th order, and that's a 1st order correction, and you do this, and you have to invert here just a diagonal matrix on a larger space than your approximation space, but it's diagonal. And here you have to do a bit more on the grid. We will see afterwards how computationally expensive this is. But this is kind of zero order, first order, and the full would be really to evaluate the A-1 on the bigger grid. Okay, so some numerical results. So first we tested it with this reduced artifact, which is known to be convex. These are the SCF iterations, that's the energy error. And you see the full error estimate, the first order and the zeroth order, they are more or less overlaid. And at some point you have stagnation of the error. You start to look at the discretization error here and split it with the SCF error here. And you see this is the error of the discretization error is here dominating at some point. And at this point you should stop your nonlinear iterations. So. Okay, now you might ask, about effectivity of the estimator. So you can take the eta divided by the thing you want to estimate. So we get reasonable, very reasonable numbers. We're not much overestimating the energy. You can ask how much is the computational overhead with respect to the full calculation. Just what is the percentage of computing the error estimates compared to the full computation time of computing the solution. So if you do really the large inversion of this operator on a bigger grid, you really have a significant amount of work balance there. But if you use this N0, which is just the first order term, you have 1%, and this is very reasonable. Then you can go to a more or realistic system. It's a silicon crystal. You don't use, or we don't have convexity. There are two different exchange correlation functionals. One is called LDA, the other PBE. It doesn't matter what it is. But the message is even the zeroth order bound works perfectly nice. And you can very nicely distinguish what is discretization error and what is nonlinear error. Good. Since I'm running out of time, I'm coming to the conclusion. I wanted to do some additional stuff, but life is always different. Then, so conclusion. One of the main messages is, in my opinion, spectral projector onto the eigenspace is the mathematically correct object to look at if you deal with eigenvalue computations. It is independent of individual choice of the eigenvectors. So if you have degeneracy, whether you have a basis like this or you turn it like this, I mean, it's still the same space and the same solution. And you have a very natural connection to the Grassmann manifold. You can develop fully guaranteed a posteriori upper bounds with the energy of plane wave discretization, so Kohn, Sham, DFT, with convex exchange correlation functional. This technique is based on lower bounds of linear eigenvalue problems and builds on this first publication where we did it for the Gauss-Pitayevsky equation. And what we see that some practical improvements makes it computational efficient without losing quality. And also meaning that it provides excellent bounds for non-convex functions. And with this, I thank for your attention.